Okay, so in our next one, again, we are simply going to ask ourselves, our carbon, well, is this a stereocenter? Yes, it is. This is a stereocenter. So we know that we are going to invert it. So we just draw everything else the same. This other one is just going to stay exactly the same. No difference there. Now this is going to be on a dash. Like that. Pretty simple. Okay, this next one, I remember the first intramolecular reaction we did, and you guys just were not happy with it. But when you are doing this type of problem, thankfully, she gave you a hint here, but if you only ever have one thing and you know it's an SN2 reaction, you know it has to be intramolecular. It just has to be. So here, what I like to do is I like to draw the word N under my nucleophile and then an E under my electrophilic carbon, because I know that's where the attack is going to happen, right? Because this is going to go loop, and then that's going to pop off like that. So now, what is the product you always make? What type of shape do you always make when you do an intramolecular reaction?
A ring.
A ring, right? So all you do is to say, start counting at your nucleophile. 1, 2, 3, 4, 5. Starting at my nucleophile till I get to my electrophile, I have 5 things. So I'm going to have a 5-membered ring with an oxygen in there. And that's my product. How did you guys do on that one? Okay, any questions?
Why is the Cl not a stereocenter? Or why is it a stereocenter if it's connected to a ring?
Because if I go to the left, I have a CH2 that's connected to a carbon, right?
Mm-hmm.
I have a CH2 that's connected to a carbon. So far, they're the same. But then this CH2 is connected to a carbon. This is a CH with a CH3. They're different.
Okay, that makes sense.
Remember, it doesn't matter how far you have to go. If I had 1,000,000 carbons to the left and 1,000,001 carbons to the right, just that one small difference is enough to make it a stereocenter.
Okay, thank you.
Yep.
So if that wedge wasn't there, would it not be a stereocenter?
Correct. Okay. Draw the mechanism for the following reaction. Show all 3 reaction intermediates. You've curved the arrows to show the movement of electrons. So what type of reaction are we starting off with? Acid 1, SN2, alkene addition. What do you think we're doing here?
Isn't the, what's it called? Hydro something?
Hydrohalogenation. It's an alkene addition reaction. So now is a good time to take a quick side note. Before you do this problem, we're going to take a quick aside, and we're going to talk about alkene reactions. Alkene reactions work on one fundamental principle, and the idea behind alkene reactions, if I draw a simple alkene, is that pi bonds are reactive. Okay, my pi bonds can act as essentially either weak bases or weak nucleophiles is a way to think about the reactivity. That's not a perfect description, but that's the way you should think about it. So anytime you have an alkene plus any type of acid, it could be a hydrohalogen acid, it could be sulfuric acid, it could be H+, it could be H3O4 hydronium. Anytime you have an alkene in a problem, provided it's just a double bond and it's not like benzene or something like that, provided it's just a double bond, what is the first step that's always going to happen?
The pi bond, attacks the hydrogen, and then the hydrogen attacks the...
Nope. All it does is that it's going to take the proton.
Oh.
That's all it's going to do in that first step. Anytime you have any type of acid, like proton in there. There are some other reactions when you do like radical additions and stuff like that. But by and large, when you just have this proton here, it is simply going to grab that proton. So Now, after you grab a proton, you have two choices. Because why would chemistry be? As one of my students said yesterday, Taylor, I like her, she's pretty funny. She's like, chemistry's a real bitch about being difficult. And I was like, you're not wrong, Taylor. This is an 11th grader. I laughed. It's kind of great because sometimes the kids will just like make noises like, and I was like, I don't care. Just like don't don't cuss. Okay. So here when we have these alkene additions like this, right? Where is the hydrogen going to go to? Is it going to be the red one or the green one? When a double bond grabs a proton. Because if the hydrogen goes here, this carbon will be a carbocation. But if the hydrogen goes there, this would be the carbocation here. So which hydrogen where do you think the hydrogen is going to add? The green position or the red position?
The one with the more hydrogen.
Yep. So the red one is what's going to be, is that my hydrogen is going to add to the carbon with more hydrogens, because when you form a carbocation, you want it to go to the secondary one, right? In the other format, you would form a primary carbocation, right? And that's less stable. So whenever you add a proton, you want your hydrogen to go to the least substituted, because the other side of that double bond is going to become a carbocation every time. So just as a practice, if I had this and I added
30 minutes were up.
1 second.
Grading for really not over the internet when you won't even turn on your mic or camera.
Okay, so what did you guys get for your product here? Your hydrogen adds to the less substituted one. Your bromine adds to the more substituted one. So anytime you have this type of alkene simple addition with something here, the hydrogen will always go to the less substituted, and whatever else here is going to go to the more substituted. Does that make sense? Questions?
That's SN1, right?
Yeah, so this is an alkene addition reaction. So whenever we're, because like in an elimination reaction, we form an alkene, right? We form a double bond. In alkene additions, we are essentially getting rid of the double bond. We are adding stuff across it, right? So in particular, this is a hydrohalogenation. That's this specific one. Does that make sense? Okay. So this is just the general rules that you need to keep up in mind. So let's go back to the other one. Let's go. Oh, that's weird. So try and work on this for the mechanism. I'll give you guys a couple minutes and I'll let you guys do it, and we'll come back to this. Okay, sorry about that. I had a colleague that I had to work with on something. The joys of teaching with someone that's teaching chemistry for the first time. I just want to be like, I'm not a professional. You're asking the wrong person. So in our first step, right, our hydrogen is going to go to the outside carbon because we have two choices here, right? We have primary and we have a secondary. So the hydrogen is going to go to the outside one, right? Because we're going to make the secondary carbon the carbocation, right? When we do an alkene addition like this, when we form a carbocation, remember this is just like when we do our SN1s or whatever types of other reactions, you always want to make the more stable carbocation. Okay, now that we have done this, what is the next step that is going to happen?
The one of like the bonds and the square it's going to attack the carbocation to make a 5 ring, like a pentane.
This is called a ring expansion. And that's exactly what you were just trying to say. But yes, that is correct. So it doesn't matter which side you, essentially it's just the bond that's moving. So I'm going to say that this bond's going to go here like this. All right. So this bond is shifting from this carbon to this carbon. So because that carbon here is losing that bond, that is going to be my new carbocation. So now, as you said, I'm going to have a 5-membered ring like this. And then you're going to have your methyl, and this is going to be your carbocation here. All right, so this is a ring expansion. What's the next thing that's going to happen?
There's going to be a methyl shift.
Not a methyl shift, because this is a secondary next to a tertiary.
So hydride?
It's a hydride. So the hydride that's here is going to just simply pop over like that. And then that's going to give me this. And then your bromine that's been chilling out here the entire time is going to come in and go. And then that's going to give you your answer like that. So how'd you guys do on that one? Where did you go wrong?
I just didn't really know how to approach it, I guess. I drew I understand like the second and the third intermediate. I just didn't know how to get to the first one.
Okay. Does it make a little more sense now?
Yeah.
Okay.
That's not one.
Any other questions?
What was the third step? Like what I did is I got all of it like right up until I think I have the plus sign. I had it somewhere else. Like I had it where like the you have that 3 and then I had the plus there, and then I just like the bromine just attacked the carbocation, and I just got the product, but I didn't do the shift that you did.
Okay. This is something that actually my dot cam, it might be easier for me to use a dot cam right now. So let me just open it up, and I think that might be easier to do because my screen is just being all sorts of stupid tonight. So let me just grab my notebook real quick. That might be easier. So now, since 3 lost my bond, what's my carbocation now? 3.
The 3.
Yep. So my 3 is now the carbocation. So now I have a secondary carbocation here, and it's next to a tertiary. So now I need to have a hydride shift like that. That's why that hydride shift needs to occur. Does that make sense?
Yes.
Okay. Questions on that? Anger on that?
A lot.
That's fair. Yep, so our first reaction intermediate is going to be the carbocation here. Our second one is going to be this one. And then our third one is going to be after the hydride shift, which is going to be this. This is reaction intermediate 1, this is 2, this is 3. So this is whenever you have a ring expansion, ask yourself the question, do I need to have one more hydride or methyl shift? And that's the way to keep an eye on it. All right. Okay, so let's go on to our next page. Predict the major products formed in each of the reactions. So predict the major products in each of the following reactions. So let's talk through each of these one by one. Do you guys want to work on them and then we talk through them? Do you guys want to attempt to solve them yourself?
Can we just talk through them?
Okay, so let's talk through them and we'll figure this out. So when we are talking about trying to figure out, predict the major product on this test, what question essentially is your professor asking you? Your professor is essentially asking you, if you get something, this is the test where you got to figure out which one of these bad boys is coming into play. All right. So what was the first thing I told you guys to think about in this reaction? Find your leaving group and figure out what type of carbon it's attached to. What is this carbon substitution? Because OTS is your leaving group. Tosylate's a good leaving group. So what type of carbon is that? Methyl, primary, secondary, tertiary. Secondary. Have I eliminated anything? Or are they all still in play? They are all still in play, unfortunately, right? Secondary carbons, good for all, okay? That didn't help us, but we move on to the next thing. I'm gonna look at what's my arrow. Okay, water. A strong base, strong nucleophile, weak base, weak nucleophile, some combination.
Can it be either?
Okay.
Which ones?
Oh wait.
You can at
Mhm.
least, so when you get something like this, you can separate them individually. Like you can have a strong nucleophile, you can have a weak nucleophile, right? You can have strong base, weak base. Sometimes you can match them. So what is water? What ways can waters act as?
Isn't it like a weak nucleophile?
Yep, it is a weak nucleophile. Anything else?
Maybe a strong base?
It is a very weak base.
Oh, weak.
General rule of thumb, this is not always true, but if something is a weak nucleophile, more often than not, it is also a weak base. That is not always a true correlation, but that's something you should think about. Water is both. So since these are weak nucleophiles and weak bases, what's going to be in competition?
Is it SN1 and
SN1 and E1.
That's correct. These are going to be in competition with each other. So how many different products can you get here?
2.
You are going to get your elimination. Actually, this is going to be a fun one. You are going to get an elimination product, right? So
boy.
like this, right? So you can have this, right? Or you can have this. You can have the SN2 product. Sorry, the SN1 product, not SN2. Like this. Or you can have the other SN1 product. Like this, where it's all dashes. So technically in this one, you get 4 products. This is where stereochemistry kind of bites you in the butt. The reason why these are separate is that this is trans 1,4. This is cis 1,4. When you give this double bond, you create 2 different stereocenters. You're going to create RNS there. That's why they're going to be 2 different things. So, but do you guys at least see that it's the SN1 and E1 products? So even what I would recommend, and this is my recommendation, is that if you're taking this test, what should you write down on the right side to help your case, to show that you know what you're doing? If you were taking this test for me, what would I recommend you guys do? Because you might have missed a product, but what might help sell your case is, I'm not a complete idiot. I know what I'm doing.
The reaction.
Right, SN1 plus E1. If you write what's happening, that might help you out. I'm not saying that's going to get you points, but remember, the more information you give to people who are applying your test to you, it's easier it is for them to say, well, you know, I can give them partial credit because maybe they forgot something like that, right? So they would be more apt to give you, if you can say, hey, this is an S1 and E1. Okay. Let's go to our next one. What type of reaction is happening now? We have H2SO4 and heat with an alcohol. Again, this type of question is asking us, any people want to tell me what is happening when we have this here, these conditions?
Is it a SN2?
Mm-mm. When you see H2SO4 and heat, you should think only one thing.
Oh.
That's Gwen's hair is going crazy.
Sorry.
No, it's fine.
It's
Is
an
it?
elimination reaction
What?
because don't the high temperatures.
You guys both said something at the same time, so I don't know what you guys said.
I don't know. You can.
I'm just confused because I thought it was the acid catalyzed hydration, but I don't know.
When you do this acid catalyzed elimination, so you're going to get that
Why is it E1?
because you are just eliminating that alcohol. Or it's not an E1, it's just an elimination reaction. It's an acid catalyzed elimination because the OH is going to take that proton and it's going to form water like this. And now that's a good leaving group. But when you see these conditions here, just know you're going to form a double bond every time.
So if we had if the problem was the answer we got for that instead of the OH, would we get for the answer would we get the OH thing? Because isn't the acid catalyzed thing don't you have a double bond and then you have water and then you have the H.
You're thinking of an alkene addition.
Oh.
This is a dehydration reaction.
Could you put the product back? I'm sorry. I was writing notes before I got to this.
You said the product? No, actually, that's not the product. Dang it. Sorry. We get to do this together forever. Yay. Okay. So we're going to do this step by step. So when I see the reaction arrow, H2SO4 and heat, you need to see both of these combinations. That delta sign means heat.